Well, I'm going to call this a little bonus video. And you can get some extra information off this bonus video. It is also a PLAE problem. So here's the story of the problem. I've got two immovable walls 1 meter apart. Now, immovable means not going to move. Then I'm going to put between those two walls a rod. And this rod, of course, has a length of 1 meter. It's made out of, what should we make it out of? (2014) T6 aluminum. It's got an area, a cross-sectional area of 0.3 meters squared. Now it's a rod, so it's got a circular. And its temperature is 25 degrees Celsius. And it's just perfectly sitting there. It's not, it doesn't have any axial load on it. Now, I'm going to tell you that we're going to heat this up to 400 degrees Celsius. When we heat this up to 400 degrees Celsius, these two immovable walls stay 1 meter apart. So here's the bonus. We all know that when we heat up a metal, it expands, it gets longer. But what is the equation for that? Well, it's the thermal expansion equation. And what that tells us is that the change in length is equal to the coefficient of thermal expansion times the original length times the change in temperature. So two things are going to happen to this rod. When we heat it up, it is going to want to expand to some new length, and the immovable wall is going to compress it back down to its original length, and that happens simultaneously. It doesn't really expand, it just wants to. Well, what we can do is we can use the thermal expansion equation to see, well, how long did it want to get? Then we can use the PLAE equation to find out, well, what force would it take to bring it back? And the question that goes with a problem like this is, when the rod is heated from 25 degrees to 400 degrees, what is the axial stress that's developed? What axial stress is developed in the rod? So here we go. Let's find out how much longer it wanted to get. Delta L equals, now where are we going to find the coefficient of thermal expansion? It's in the back of the book. The very back cover, where it lists all the materials, the last column is coefficient of thermal expansion. 2014 T6 has a coefficient of thermal expansion of 23 times 10 to the minus 6th with units of degrees Celsius to the minus 1. So delta L equals 23 times 10 to the minus 6, we'll put the Celsius down below, times the original length, which was 1 meter, times the change in temperature, 375 degrees Celsius. Look what happens to the units. We're going to get an answer in meters. 23 times 10 raised to the negative 6 times 1 times 375 equals 0.008625 meters. Now that tells us how much longer it wanted to get. Now we're going to use the PLAE equation to see how much shorter, or how much force does it take to make the beam, the rod, shrink by 0.008625. So we're going to solve this for P, and actually, if we solve it for P over A, that will be the stress. So let's solve it for P over A, which will be the stress, which is going to equal delta times E over L. And what's the delta? 0.008625 meters. What is the modulus of elasticity for aluminum? And I get 73.1 times 10 to the 9th pascals. 73.1 times 10 to the 9th pascals divided by the length, 1 meter. So let's do this math. Equals 0.008625 times 73.1 times 10 to the 9th divided by 1 equals, that's a big number, 600, I just got to write it all out. So the stress developed in this rod when we increase its temperature by 375 degrees is 630487500. Well, we got a comma there and a comma there. 630 megapascals. 630.5 megapascals. So the stress, is 630.5 megapascals. Wow. All right, well, there's your bonus video. It was a PL over AE problem where the temperature increase made the rod want to expand, but the force of the immovable walls prevented it from expanding. The amount that it gets prevented is exactly equal to the amount that it wanted to increase. And when we solve that for P over A, we'll get a stress of 630.5 megapascals. There you go. Have a nice day.